Hi there, welcome to another presentation of a tutorial exercise. My name is Charles Wells-Fanamsipo. Today I would like to discuss the following exercise with you. We are given a function f of z, complex function f of z, e to the power z squared. So we are required to use Cauchy Riemann equations to determine whether the function f of z is analytic, and if so, we determine the first derivative fz prime in its simplest form in terms of z. So let's start this way. First of all, given an exercise like this, we should reflect what we have here. In this case, we've got a complex variable z, which is equal to x plus I, y, and as we have, we've got an exponential function, and its argument is z squared, which we've seen before. This simplifies to x squared minus y squared plus 2x y I, that is squaring this binomial z, which is written in terms of x and y. So remember that if we're going to use Cauchy Riemann equation, we should first of all also be able to express f of z in terms of two variables x and y, given this way: f of z equals to u of xy plus imaginary unit times v of xy. Now we know that this is our initial step. I would like to label it here initial step by 0. So we also know that Cauchy Riemann equation says that if a function is analytic, we should have delta u delta x equals to delta v delta y, and I emphasize and, as the two conditions are satisfied, and delta u delta y is equals to minus delta v delta x. So now, having this, now we can start in our first step. Now let's label here 1. Let's try to achieve to get f of z in this form in terms of its conjugate functions u and v. So we're going to express here f of z as e to the power z squared, which is equals to e to the power x squared minus y squared plus 2xy I. Now, simplifying this, moving towards having f of z in this form, I think you can see here that applying rules of exponents, we can write this as e to the power x squared minus y squared multiplied by e to the power 2xy I. And using recalling this identity, e to the power I theta, where theta is supposed to be an angle radian, simplifies to cos theta plus I sine theta. Because of that, here we're going to have this further simplified to e to the power x squared minus y to the power, so minus y squared, in brackets we're going to have cos 2xy plus imaginary unit times sine, that is according to this identity. I think we'll see here that at this stage now we're closer to this form of f of z, so we need to distribute this factor here, there, and there. Then we're going to get our u and v. So we've got here e to the power x squared minus y squared cosine 2xy plus I e to the power x squared minus y squared sine. Now the next step is to identify our conjugate function, which is u xy equals to e x power x squared minus a squared by cos 2xy. And our v of xy is equal to e to the power xy minus y squared times sine 2xy. So now I think now we can now move on to try to do this test, differentiate and do this comparison to establish whether the function is analytic or not. Let's get this step number 2. Now let's get the partial derivative of u with respect to x. Now we note that now u here as a function of x is a product. Now it is exponential function minus this cosine, which is a trigonometric function. So we're going to apply the product rule for differentiation, the usual product rule for differentiation, which is going to be, we recall that the exponential function, when it's differentiated, it comes back exactly as it is, multiplied by the derivative argument, which in this case is going to be 2x. So multiplied by cosine 2xy plus, now we're going to differentiate cosine, which we know that the derivative of cosine is minus sine. So we're going to have a minus here. The derivative argument in this case is going to be 2y multiplied by e to the power x minus y squared sine 2xy. I hope you can double check that and see whether I'm doing that correctly. I might have a slip of pen here and there, but must check and actually follow the method very carefully. Now the next thing, let's get to delta v delta x. I've just decided here to start with partial derivatives to x, so that's not a problem. So doing this, it's going to be a similar derivative to this, which is going to be 2x e x squared minus y squared sine 2xy. Now differentiating sine, the derivative argument is going to be 2y again multiplied by exponential to the power x squared. That now this is going to be cosine 2xy. Now let's move on and do the partial derivatives with respect to y. Now delta u delta y. Now the good thing here, these derivatives in structure they're very similar, so it's going to be easy to do that. Now we're going to replace this by the derivative of the derivative of minus y squared, which in this case the argument of the exponential function with respect to the variable y, which you are differentiating with. So you're going to have the minus 2y, the rest is the same, x squared minus y squared cosine 2xy. Again here is going to be minus, now it's going to be 2x 2x e x squared minus y squared as sine 2xy. I think you can note that here I'm just mimicking this same derivative with respect to y, so it would be nice if you can organize your work properly, then it helps you to get this derivative quick. Now turning to delta v delta y, we will first differentiate this function with respect to y, which is going to give us minus 2y e to the power x squared minus y squared multiplied by sine 2xy plus, now we're going to differentiate sine with respect to y, and then the derivative argument is going to come up with says 2x, then write here 2x e to the power x squared minus y squared cosine 2xy. Now we need to proceed to comparing these derivatives and see if the Cauchy Riemann equations are satisfied. So let's do this way. We start by comparing delta u, delta x with delta v, delta y. So we note that here delta v, delta y is exactly the same expression as we have there, except that they are written in a different order, but we know a plus b is equal to b plus a. So this is equals to 2xe x squared minus y squared cosine 2xy minus 2y, which is this term, e x squared to power x squared minus y squared sine 2xy. As you can see, this is clearly equal to delta v delta. Now let's turn to comparing the other two derivatives, which are delta u, delta y, comparing with delta v, delta x. Now we've got here delta u, delta y is minus 2y e to the power x squared minus that cos that, and we have minus 2x e to the power x squared minus y squared sine that. Now if we compare with this derivative, it looks like there's something a bit wrong here, because the signs are not really opposite sign. Let's see what could have happened. Let's check what could have happened here. So here we expect this to be equal to minus delta v delta x. Then let's just double check the partial derivative with respect to x. We have here v differentiated with respect to x. Let's check what it gives us. The first one gives us the derivative argument of e, 2x, that, and the sine. Then when we come this side, we're differentiating sine ahead. There is the mistake. There was a slip of a pen there. This is supposed to be a plus sign. With that, now I think it is clear that these two derivatives are exactly the same. Like this term, we have it here, and that term there, they differ by the sign. And similarly, this one and that are exactly the same, they differ by the sign. So we can say here, this is minus the derivative of v with respect to that is 2x ex to the power x squared minus y squared sine 2xy plus 2y e to the power x squared minus y squared cosine 2xy. So you can see that these are actually, they differ by the signs. So now we can say, conclude now that therefore Cauchy Riemann equations are satisfied, and that means that our given function is analytic. Then we can now proceed to compute the derivatives. Let's decide to compute the derivatives with respect to the partial derivatives with respect to x. In this case, we're going to grab delta u, delta x, and delta v, vector x. Now, having these two partial derivatives respect to x, we know that fz prime will then be equals to partial derivative of u respect to x plus imaginary unity multiplied by the partial derivative of v with respect to x. So what we're going to do now is to rewrite this. Let's reorganize this and write it as a 2 e to the power x squared minus y squared brackets x cosine 2xy minus y sine 2xy plus the imaginary unit. Reorganizing that again, we can have let's put a bracket here, square bracket, then others there. Then I'm going to have brackets x sine 2xy plus y cosine 2xy. So by so doing, I've avoided repeating this exponential expression 4 times because it's a common factor, and the 2 is also a common factor. I've drawn that outside there. Then now we can start reorganizing this. At the moment, we should be focusing on what we know, and our simplification here must be guided by the fact that we know that if the function is analytic, like we've got e to the power z squared, and we've established analytic, we know that the derivative will assume the same structure like one word when we're dealing with functions of ordinary variable. In this case, it's going to be 2z e to the power z squared. So that must guide us in the simplification of this expression. So let's now rewrite this as 2 e to the power x squared minus y squared. Let's collect the terms which have got x. In this case, we've got this one and that one. Then we're going to have here common factor x, and we've got cosine 2xy plus I sine 2xy, and then for y we're going to have y cos 2xy, and then we collect this one. So this one's got an I here, and there we've got a minus I, which is actually plus I squared y sine 2xy. Actually, you could have, so this is I squared. Could have taken our y out as a common factor. So let's rewrite this as y in brackets I cos 2xy plus this minus sign here. Let's write it as I squared sine 2xy, and that, recalling that I squared is always equals to minus 1. So proceeding here, I think you can see that here we've got an I common factor. So what we're going to do here is to take out I as a common factor, which will give us I y. Then inside here we've got cosine 2xy plus I sine 2xy, and then continue with our square bracket there. And here we've got x cos 2xy plus I sine 2xy, and our exponential 2x squared minus y squared. Now let's correct this a bit. That is 2. Okay, now I think we can see that we've got a common factor here, and this common factor there, and then we're going to remain with x plus I y. So continuing with that, what you can now do is, and remember also this we can write as e to the power, these two terms, we can write them as e to the power I to x. So what we can do now, we can say 2e to the power x squared minus y squared in brackets. Because this is a common factor, let's take it once outside is e to the power 2x y I. Then we are left with the x plus I y, and that. I think now it's clear that now we can multiply this, and then now applying rules of exponents between these two exponential functions, we're going to have 2, and this is a z, so we're going to have a z to z e to the power x squared minus y squared plus 2x y I. And right at the beginning, we recall that this expression is the expression of z squared. So what we have now is exactly what we want. In this case, we're going to have here 2z e to the power z squared, which is our derivative in its simplest form in terms of z. So I would like you to invite you to calculate the same derivative now using the partial derivatives with respect to y, which in this case f prime z will be equals to delta v delta x minus the imaginary unit delta u delta y. I think doing this exercise is a good practice of tracking detail or doing calculations carefully, and make sure that you get used to this kind of computation. Otherwise, for now, thank you for listening. I hope this example helps.